Hi everyone, and welcome back to a new episode. Today we're talking to Laurent de Parny, and this is going to be a two-part discussion where we're going into the details of quantum information networks and the associated architectures. As I said, this will be a two-part series, and this is particularly the first episode of that series, so enjoy this one and then stay tuned for the second episode as well.
Okay, so I'm working at Thales Alenia Space in France, and we are working on quantum communication, and particularly we're working with satellites, because on quantum communication the satellites, as I will explain, has an important role. And so I am system engineer, but I joined industry, but before joining industry I did a PhD in theoretical physics. And I was working on a quantum phase transition, and so I had developed the skill to manipulate quantum stuff. So first, just a very quick recall of what is quantum. So quantum, the quantum physics theory has been developed because it was not possible to explain what is an atom and how an atom works. And also the radiation from when you hit material, it as you know, it emits light, and the light, it was not understandable at the beginning of the 20th century. It was not understandable why such material was emitting the light. And also, as you know, we are speaking about particle and wave. So in fact, a particle is also a wave, and the wave is a de Broglie wave. And so this is purely quantum. You cannot understand this behavior of the matter with the classical physics. And also the Tunnel effect that is used in transistors, and Meissner effect, and so on. And so I have two photos of the lab where I did my PhD, and here in blue, the blue bubble is in fact quantum atoms at a very low temperature, roughly 100 nanokelvin, and at this temperature the atoms, which are particles, behave like waves, and you can see the wave nature of the particles at this temperature, and that's very surprising. So this is called the Bose-Einstein condensate. Okay, so that was just to recall what we called quantum. All this behavior are explained by quantum laws of physics. But in fact, so you have contacted me because I'm working on quantum communication, and it is important to note that we are now at the second quantum revolution, but before the second quantum revolution, there were, of course, a first quantum revolution, and everybody knows, in fact, the outcomes of this revolution, because everyone now have a computer, and we are all manipulating lasers also, and so this is two devices that are outcomes of the first quantum revolution, when you're manipulating flows of quantum particles, so like electrons or photons for the laser, and so this first quantum revolution has now an impact on our life, and since the beginning of the 21st century, we are at the second quantum revolution, where we are now able to manipulate single particles, so single quantum particles, one by one, so like one electron, one atom, one ions, one photon, and this brings, in fact, novel properties that we are exploiting. And this is what we call the second quantum revolution, and it brings quantum processors, quantum sensors, and quantum communications. And we
quick question on that. So
yeah?
on the characterization of the second quantum revolution, would you say it's fair to characterize all of these applications as part of that second wave? I'm thinking particularly when it comes to timelines, because communications, as we will get into,
Yeah.
some of these applications have very long timelines before we think that the solution would actually be feasible. Would you say all of this is sort of still categorized as one bucket, or would you say a more fine-grained division is probably at place here?
Okay, so well, it depends. So if you focus on the quantum communication part, we now have devices that emit single photons and also single photon detectors. So we are able to manipulate single photons, and you can buy it on the market. There are companies that sells this device. So this is a real market now. But of course, so everybody knows what is the internet with a laser. We are using laser for the classical internet, and we are far from using single photons on such networks. So we have to develop quantum networks to use and exploit all these new effects, of course. But one promising use case is quantum key distribution. So we are not so far from developing this kind of networks, in fact. Mm-hmm. But for quantum teleportation, we have to work harder to reach to attain such use case.
Mm-hmm.
Yeah,
okay.
I will come
Maybe
back
we'll
on
get back
this,
to that on the exactly.
Yeah, sure.
Yeah.
But still, this is an important question, because when people are interested by this, so typically people ask the question, okay, I have internet in my home at home, and when we'll have access to this quantum information network. So is it possible for me to be a user of these networks, or should I wait a long time before I can access to these new use cases? And this is not easy to answer, but what I observe now in industry is that there are more and more companies that are developing this quantum device, and there are big companies that are developing the infrastructure. And we have customers that pay for that. Yeah. Yeah, okay, and so in these networks we are not manipulating bits. So bits, as you know, this is 0 or 1. So in quantum information networks we are manipulating quantum bits. So quantum bits, we call this Q bit. So quantum Q for quantum and bit for binary digit. And we are exploiting the fact that in quantum mechanics a system can be in a superposition of state. So you know, in physics, the Schrödinger cat. So Schrödinger has thought about an experiment with a cat, and he said that if the cat were quantum, it could be dead and alive, which is a paradox, because as everybody knows, we are either dead or alive, but not in the two states, because the states are orthogonal. You cannot be in these two orthogonal state, and in fact, if you are quantum, you can, and this is typically what we call the superposition of state. And the superposition of state is used, for instance, in the D-Wave computer. So D-Wave is a company that sells one type of quantum computer, which is called a quantum annihilator, which is good for finding the minimum of a function. So you can enter a complex problem and ask what is the better solution. So this is optimization problems, in fact. And this computer, for instance, is using 2,000 qubits, and that means that you can reach 2 to the power 2,000 possible solutions simultaneously. And so that the power of this computer comes from the fact that you are manipulating both 0 and 1. So in fact you are manipulating a vector on the sphere, so a point on the sphere, and the point, so you have a much denser possibility to exploit than just a qubit composed by 0 and 1. And to explain very briefly how it works, so these new effects, the qubit, you cannot, it's not easy to produce, at least in such a computer. It's not easy because you are exploiting superconducting effect, so you have to cool down the temperature such that the processor works at 15 millikelvins. So this is close to the absolute zero. And then you have cool effects that emerges. So you have cool effects that emerge from. So these cool effects are quantum effects, as you understood. But the problem is that in this computer, you have to isolate the qubits. So they are using superconducting metal niobium. And so to observe this qubit, to generate these qubits, you have to isolate the device from the environment. And so you have also to isolate with a shield, with magnetic shields, to reach very low magnetic field. Otherwise, it can disturb the quantum processor. And
just a quick question on this: are we specifically talking about superconducting architectures now, or are we talking broadly speaking for multiple quantum computer architectures?
Okay, so in the D-Wave, so I'm not an expert in quantum computers, but this is just to introduce that if you want to observe and manipulate quantum qubits encoded in the superconducting metal niobium, you have to cool down. So I cannot
fine.
be precise in the architecture. So I know that the architecture is very complex. At the moment, there are many actors. So we are speaking about D-Wave, but there are many actors working on this. In France, we have new companies like Alice and Bob, Pascal. We have also Candela for optical quantum computer, and of course all the big companies in the US like IBM, Google, and and many other actors. So there are a lot of quantum computer types and architecture. But what I can say is that there are no universal computers that can be used to be used for generic algorithm, let's say. So you can do particular task with each type of architecture. So the universal quantum computer does not exist. Yeah, so I was speaking about IBM. So IBM is now working with a quantum computer called System 1. And so they can reach 127 qubits with the Eagle processor. And they are improving the capabilities of this computer. And the problem is that the quantum states are very fragile. And so when you include more and more qubits, you include more and more opportunities for the qubits to be disturbed. And so at some point you reach the classical world in which we are in fact living. We do not see the quantum superposition of state, for instance, because we are in the classical world, and the classical world, which is purely quantum at the very beginning, the classical domain arises from the decoherence effect that you tend to when you increase more and more qubits. So this is very difficult to maintain the coherence of the qubit, and so there are error mitigations, and we have some strategies mitigation strategies. I mean, to go further, but people who are working on this are fighting a lot on the decoherence effect. Yeah, and also very recently, so we saw that Russia has its first quantum computer made of trapped ions, with the 15 ions. So also Russia is involved, US, France, China, all the big countries are involved in this long run to develop the quantum computer.
Mm-hmm.
Okay, but if I go back to the subject of my talk, so I said that we are now in the second quantum revolution. We are developing quantum devices, so I was discussing quantum processors, but there is also quantum sensors, so Thales Group is involved in this, for instance, for developing very sensitive devices. So we can think about clocks, for instance, atomic clocks. In the Galileo satellites, we are using this, for instance, and also magnetometers, accelerometers, gyrometers, gravimeters. So the main idea of the quantum sensors is to develop devices that are able to do measures, very precise measures. And the third topic, which is the subject of this talk, is the quantum communication. And so we can find some commercial device now. If you look at Huawei, Toshiba, ID Quantic, or Aurea in France. So we have many providers for this. And the target use case are quantum cryptography, certificates, vote, auctions, crypto money also, and for the future information networks to connect quantum devices all together. So in what we call the quantum internet, to think about many quantum devices that are connected all together. And
when we talk about players in the space that are currently fabricating technologies, are you specifically talking about quantum key distribution then, or are there other aspects of quantum communication in general where the technologies are far along enough so that you have big players actively sort of pushing technologies toward that space?
I think in space we are definitely the leaders. There is also Airbus Defence and Space, but I think they are more involved in the quantum key distribution, because in fact we realized when we're starting to work on this topic that QKD, quantum key distribution, is the first use case that we will reach. So definitely the Chinese, for instance, with Micius, shown that this is possible to perform space QKD, and so it has opened a new perspective for space actors to work on this. But we are actively involved in the second step, so we are going further in Thales Alenia Space. We are focusing on the quantum information network, that, by the way, can also be used for doing QKD, but based on entanglement, in fact. But you can also go further and connect quantum sensors or quantum computers all together. So this is definitely more interesting, but more complicated also.
Mm-hmm. Can you maybe summarize the key benefit that a quantum information network would provide compared to existing networks that are based on classical technologies? Is it easy to define one of those deliverables that really quantum information networks can do a lot better than existing networks, or is that also something that's sort of hard to articulate at this point, and we need more technology to even be able to say what benefits we're going to gain from quantum information networks? Yeah,
okay, so one benefit, so I was speaking about QKD. So for quantum key distribution, one benefit is to generate shared keys to encrypt our communications for the security of the communication, because the problem is that what we are using at the moment mainly, so this is called RSA, so reverse Sherman-Adelman. So this is a protocol that is in danger due to the quantum computer. So there is a threat. The quantum computer can attack the way we encrypt our communication, and then decrypt the message, and that's a big threat that is identified. And so this quantum information network, if you think about security, QKD is one solution. is one solution based on quantum effects. And so if an eavesdropper listens to the communication, this attacker will not be able to retrieve the plain text message. So this is one advantage to develop quantum information network. The other advantages are that when we will be able to manipulate, to play with quantum computers, the need to connect them all together will be clearly the need will be identified, I think, very fastly, because as if you think about what we did for the classical computer, we have developed computer, and very fastly we needed to connect the computers for communication, and I think that for the quantum computer the need will be the same. And so the problem is that you do not manipulate 0 and 1 encoded on billions of electrons or billions of photons. You are manipulating a superposition of 0 and 1 encoded on one single particle. And this is new rules. So all the internet we are using will have to be rethink. We should develop new networks. So the quantum networks are completely new. So that's why we call them quantum internet, but this is very misleading. So we don't like to use this terminology. We prefer to speak about quantum information network because we are manipulating new stuff, so the qubits, and so the rules are completely new. And so as I will explain in a few slides, you will see that when you want to send a qubit, you have to teleport the qubit, and that's completely new. So that's the other advantage, to put in a networks many quantum computers. And what I didn't say is that also so depending on how you connect them, you can increase exponentially the power in terms of capacity, of computing capacity. You can increase exponentially the capacity of the device you connect in a quantum information network. So that means also increase exponentially the power of your devices. Yeah, so that's why we are interested in this, in fact. But there is a problem, and that's important, because now I will explain why a space actor is working on this. So space actor means satellite, and in fact, when my boss starting to work on this topic, they realized fastly that we cannot connect quantum device at the ground with an optical fiber more than roughly 150 kilometers. So because in the fiber you have absorption, and you cannot amplify the quantum signal, because if you amplify the signal, you destroy the qubit. So you cannot use amplifiers as we are doing in optical communications, in classical optical communication. So since we cannot amplify, we have a problem for putting into a network quantum devices at long distances. And so that's why the satellite is mandatory, and that's why I'm working on this topic at Thales Alenia Space.
Can you explain why the satellite actually helps to resolve that? So we'll get into the details of this in a second, I suppose, but we're talking about quantum teleportation in general. So we have a qubit, we're going to teleport it to some other state, and we're going to do that by means of a satellite.
Yeah.
What is the reason why the intermediary needs to be a satellite? Couldn't you have, let's say, Earth-based stations where you would have quantum teleportation set up, and we'll get into the details of how that works, but nevertheless, what is the use case of actually having a satellite that contains or facilitates this transaction?
Yeah, so here this is exactly the slide which answers to the question. So why are we using satellites? So that's not obvious to understand why a link from space to ground is better than links from ground to ground. And so this slide explains that in free space we think that so naively we can think that there is a beam divergence, so we will lose photons. If you send photons, the beam diverge, and so you're losing photons. There is also absorption in the atmosphere and scattering. So all these effects will increase the losses. So technically we are speaking about a link budget. So they will increase the losses, and so they will decrease the link budget, in fact. And in optical fiber, we have absorption. We have mainly absorption, let's say. And this figure is very interesting. So I took it from the paper, from the Chinese paper published in 2017. And they compare, in fact, the link budget from space to ground. So the blue here, this is space to ground, from the satellite to the ground, and the red is what we obtain from ground to ground with an optical fiber. And so with respect to the distance, here you see that when you increase the distance, you increase the losses, of course. And if you look at 1,200 kilometers, you have roughly 200 dBs of losses in a fiber. So this is very huge. So the Chinese show that if you are using their device, their quantum source and their quantum detectors, you have to wait 27 times the age of the universe to observe one detection. So at ground, it is not possible to use an optical fiber for performing an quantum optical communication at this distance. That's not possible. So you're stuck. And the solution is to use the satellites, which has a much better link budget. So it means much lower losses. So if you compare at 1,200, you have 20 order of magnitude between the two solutions, and so the link budget is definitely much better from the satellite to the ground. Because in fact,
do you have a conceptual understanding for why the losses in free space transmission are so much lower compared to optical fiber in these cases? I would have expected it to be the other way around, honestly, if I just think about it conceptually. Do you have some form of intuition why that's the case?
Yeah, so why? Because the main disturbance effects are in the atmosphere. So of course, if you have clouds, definitely you have no signal. No? So this comparison is performed assuming that you have no cloud. Okay, because if you have a cloud, the signal. So it depends of the wavelengths, but we can say that when you have a cloud, whatever the wavelength is, the signal is stuck. It is stopped by the cloud. So the main perturbating effects are in the atmosphere, and the atmosphere is roughly at the first tenth of kilometer above the ground. So that means that the first losses you have from the satellites up to the lower layer of the atmosphere are mainly due to the beam divergence. And the beam divergence, you can reduce it by considering a big telescope at the satellite level. So the bigger the telescope on board the satellite, the lower is the beam divergence. So you can reduce these losses. But of course, in the atmosphere, you have absorption, so it depends of the wavelengths you use, and you have scattering. But if the source is generating 1 billion of photons per second, you have a lot of losses. But sometimes you you are able to measure one photon coming from the satellite, and then this will be a useful resource for the quantum information network. Yeah.
Okay, so the main difference is that for the majority of transmission, there would be no disturbances, essentially. It's just the atmosphere that's messing this up, and that's only for a few kilometers at the end. Okay.
Yeah, and the problem is to work with cloud. So you have to think about operations in two times. So you have to think about the first time the satellite will generate the quantum resource at ground. The quantum resource is stored at the ground, and then is used by end users on the demand. Because if you are a user, you don't want to wait clear sky to have quantum internet. Okay, it's not possible. So the end user will, wants to request quantum resource and to obtain the quantum resource when they request it. And so this is real-time operations. So we have to distinguish these two phases where the satellite is distributing the quantum resource. The quantum resource is stored at the ground when there are no clouds, and then the second phase of operation allows the user to access to the quantum resource on demand. So that's not easy. Yeah. So if I just go back to this, okay, maybe I will comment this very briefly. So this slide shows that there are these two targets. So the first target of use case is for quantum cryptography, so QKD. So QKD means that you are using quantum laws to generate shared confidential random numbers that are just 0 and 1 at the end. So what you share at the end, this is classical keys, classical bits, 0 and 1. But this is a sequence of 0 and 1 that is the same for Alice and Bob. And then they can encrypt their communication. And here is the other use case to share quantum states, or to share entanglement, in fact, to connect two quantum devices that are located far away. At least when you are using a satellite, you are targeting two users that are far away.
And is it a general principle of all quantum information networks they want that to have zero latency, essentially? So we're going to talk about the tunneling later, or the teleportation of quantum states. Is it generally a feature of all quantum information networks that this communication needs to be instantaneous, or are you allowed to also have some lag in that transportation?
Yeah, okay. Yeah, so I will explain why the quantum teleportation is not instantaneous.
Okay.
So you cannot you cannot communicate faster than the speed of light. So Einstein is safe for many reasons, but at least like in internet, a user wants to reduce the delay. So this is what we observe, for instance, with Elon Musk on the Starlink constellation. He is developing a low Earth orbit constellation, so that means satellites very close to the Earth, because it reduces the delay of the internet, and so we are also targeting such orbits and constellations of quantum satellites for this kind of use cases, for the quantum information network. So we have performed many calculations from end-to-end system calculations, system assessment, and we definitely target low Earth orbit constellation to perform such use cases, to allow to access to these use cases. Yeah, so by the way, about the use cases, so we have published a paper in Nature Communication Physics this year, and you can read it. This is online and in open access, and we discuss the new use cases for industry, for critical infrastructures, finance, administration, and also for science, operational and fundamental science. And so we have summarized with our partners many use cases that these new quantum information networks will be able to provide.
Mm.
And so I can say a few words about Michou satellite. So the Chinese they have performed very beautiful experiments with this satellite, and this is a 600 kilogram satellite in low Earth. So low Earth is typically 500 of kilometers, and this satellite was equipped with 4 payloads to perform many experiments. And so the satellites look like this, where you can see 2 optical terminals. So one was 30 centimeters and it was fixed to the platform, and the other one is 18 centimeters diameter, and this one is a turntable. So it means that you can move it. Yeah, because
is this somehow related to the prototype
Yep.
that you were referring to in the paper, or this particular satellite? How does that fit into the wider context of the quantum information networks?
Yeah, so in fact it was like a Swiss knife. You have many possibilities, many experiments that you can perform on this. And with this satellite, so there are 2 telescopes, as I said, a smaller one and a bigger one. And these 2 telescopes were used for different applications, different use cases. So they used one telescope to perform prepare and measure quantum key distribution, because the prepare and measure protocols is using just one single quantum link. So you are not using 2 telescopes at the same time. Just one is sufficient. And so they realized such experiments on quantum key distribution, and they have also generated untangled states on board, and they have sent untangled states to the ground. And entanglement is very important in the discussion we have now, because this is the main resource, the main quantum resource that we need in a quantum information network. And so the satellite is generating this quantum resource and is sending this resource to the ground. And entanglement was a Nobel Prize in 2022. So we have a French researcher, Alain Specht, who won the Nobel Prize, and it is based on this work related to generating entanglement.
Mm-hmm.
And so now we are able to...
Yeah, I guess we can talk about that as well, but I think you have a
Yeah.
slide on that coming up.
Yeah. Okay, so I will not comment in detail this slide, but it's just to show that we are at the beginning from the space demonstration, but still the people have worked on this, and so there are concepts in this slide. There are concepts, but not only. For instance, Chinese before Michou's did some experiments with balloons, also drones, and there were very interesting experiments with. It was also on the ISS. Our colleagues in Italy has performed also communication with retro reflector on space. So they send a qubit, and the qubit is coming back. So they have published some experiment like this. There is also Spooky, performed by Singapore colleagues, and Socrates by the Japanese. And all this worked, and they have also, so the NASA has also used planes to generate entanglement and send it to the ground. And so all these experiments convinced that we can go further, and we can access to the space segment to generate quantum resource and send it to the ground.
Mm-hmm.
Yeah, and now Chinese have a quantum network, so I think Misuse is not operating now, but they have launched another satellite called Jinan 1 last year, and Jinan 1 is specifically designed for QKD. And so that's interesting because they have developed a ground network and a space segment that is connected to the ground network.
Mm-hmm.
So
I see that all of these applications are related to QKD. That's somehow different from the quantum information networks in general that we're going to be talking about, right? Do you have any parallels? Like any parallel missions that have been, or prototypes that have been tested as of now already that are not solely focused on QKD, but general quantum information networks?
Very interesting question, because you know, most of my time when I'm speaking with people, they are all focused on QKD. So and why? Because QKD is we can say that this is the first step to go towards quantum information networks, because QKD it pushes us to develop single photon detectors to manipulate the quantum encoding variable like polarization or time being. So there are many quantum encoding variables, and so QKD is good to go further step by step. But that's true that most of the people are speaking about QKD, and I would say because this is the first step in terms of complexity. Mm-hmm. So I know that people in ICFO in Barcelona are working actively on quantum information networks. We have our colleagues in France also, the Sébastien Tanzili group and Hélène Diamanti also, they're working on this. And in Delft, in the Netherlands also, they are very active on such networks. But this is more complicated. There are more complications to deal with. But that's why this is also more interesting, I would say. Yeah, so to answer your question, most of these experiments are related to QKD.
Okay, understood.
Yeah, so now we can discuss, so it was like an introduction, a long introduction, but so now we can discuss what is the quantum information network. Mm-hmm. So when you ask to someone, to imagine that two people have two quantum computers, so Alice and Bob, if they want to connect one with another, what are the possibilities? So the first is to say, okay, just connect them with an optical fiber at ground, and so it can work, of course. But if Alice and Bob are close together, so when I say close, is typically, roughly speaking, 150 kilometers. Okay, so that's nice. If they are close, that's nice because optical fiber exists and you can perform real-time communication. But the problem is that if they are far away, that does not work anymore. So if Alice and Bob want to share a qubit, and if they are far away, you can think about another possibility, such that Bob send a qubit toward the satellite. So you assume that you have a quantum memory on board the satellite, and the satellite just evolve, so it is orbiting around the Earth, and at another moment, so T2, the satellite can just emit the qubit to Alice, and Alice retrieves the qubit, and then you have an exchange between Alice and Bob. But the problem with this, so you have a large scale network, so that's nice, but the problem with this is that the quantum memory does not exist, and particularly for space applications, we do not have at the moment space quantum memories. And
what's the reason What's the reason for putting space into that sentence? So, do we have quantum memories that are sort of applicable to Earth and where the infrastructure requirement is so big that you can't put it in a satellite? Is that the current limitation, or what's the reason why we say that we don't have it for space quantum memory?
Yes, so first, quantum memories are now on the lab. So in industry, we often use the term technical readiness level, technological readiness level, so TRL. And the TRL is very low for quantum memories at the moment at ground in labs. So that's one problem. So we just have prototypes, and we cannot store qubits during a long time. So if you look at what is published on the literature, we are speaking about microseconds, and the qubits also suffer from decoherence effect, and so the fidelity. So the fidelity, that means that the qubit enters in a state and goes out in another state which is close to its initial state. And the fidelity is the overlapping between the output and the input, let's say. And so that means that the qubit is not exactly the same, and the fidelity decreases with time. So that's a problem.
Mm-hmm.
So I mean, if you think about an experiment with this, where someone send a qubit on a quantum memory, even at ground, the problem is that this experiment has a very low technological readiness level. So even at ground, it's very complicated to do this up to 1 second storage. So you cannot store 1 second. So that's a problem.
How come that's the case? So I spoke to someone who was working on trapped ion quantum computers, and my understanding is when it comes to those particular architectures, trapped ion ones, the decoherence time is actually quite long. So for good trapped ion systems, my understanding is that's well beyond, let's say, a second. Is there what's the reason why these quantum memories now have such poor decoherence times, essentially, even in the lab?
Yes, because typically when you're speaking about photons, the photons enter into an atom. So there is in the atoms you have two energy levels, and the difference in energy should correspond to the wavelengths of the photons. So then you have a resonance effect, and you can store. So the photon can enter into the atom and excite the atom, and then you can store the photon into the atom. And the problem is that you have to control when you want the photon to go out, and so people have used so I don't remember it, IFT effect, I think, that allows when you send a laser into the atom, then you can extract the qubit from the atom just by applying a laser into the atom. And so this effect, I think, is not well controlled, and if you think about the space applications, that's even worse, because the space environment is very complicated, because you are in the vacuum. You have strong thermal gradient, because when the satellite is in the nighttime, it is very cold, and when the satellite is exposed to the sun, it is warm, and so you have to deal with thermomechanical constraint, and that's very complicated to put a ground device into space. There are many complications, and also the device should survive the launch, because the launcher induce very strong vibrations, and so sometimes the device just die when you send it into space. So you have to think about all these effects, And so what I just want to explain is that the quantum memories are not mature at the ground, and so putting them into space is a challenge, in fact.
Mm-hmm. Okay.
Yeah, and so even if you assume that you have a perfect quantum memory, so you can think about it, the problem is that you cannot have real-time use case. Okay, because Bob send his qubit at time t1, and then you have to wait time t2 for the qubit to go down to Alice. And so you cannot communicate when you want. You have to wait that the satellite goes up to Alice and that there is no cloud, such that the photon can be sent to Alice.
Could you not introduce the second satellite into the system? So let's say you have satellite 1, which is being uploaded to by Bob, and then satellite 1 sends its information to satellite 2, which is already in the proximity of Alice. Is that something that would work, or is that a problem from the perspective of, I don't know, some technicality?
Yeah, so this is a good reflex to think about many satellites that are connected. So we know to do this in the space industry, and for instance, Starlink is doing this now. They are using what we call the optical inter-satellite link, so OISL. But in Starlink, this is purely classical, of course. There is no quantum effects on this. But then the satellites have some optical terminals, like telescopes, in fact. And the telescopes are locked by pairs, and they can exchange light, and so they can discuss. We can encode information into the light and do an optical communication. And so that's very good reflex is to think about to use many satellites with connection between them. But okay, the problem is that if you do this, you increase the chance to lose the photons, because that means the photons has to enter into quantum memory 1 and then to be sent into satellite 2 with quantum memory 2 and so on. And so this is a chain where you have more and more quantum device where the photons has to go through, and so the efficiency goes to the power up to the power of the number of satellites, in fact, so it decreases. So that's the problem.
Mm-hmm.
And so the other way is to use quantum teleportation, because you can reach a non-limited range, so global connectivity, but still you have to develop quantum memories. So, but you can put them at ground. So that's the good message here, is that if we have good quantum memories at the ground, then we can work, we can do something, and then we can reach the real-time use cases by sending the entanglement in a non-real time, and then to exploit this new resource, the entanglement resource, to generate real-time services at the end. So
how come we need a quantum memory even though it's ground-based for these kinds of applications? So very naively, I would say you're sending a qubit. So long as you're able to teleport that instantaneously to the other system, there would be no need for storing that inside a quantum memory. Obviously, there's something I'm missing in this picture, but could you please explain why that's not a feasible solution?
Okay, well, in fact, in the paper we have published, we were thinking about first experiment in real time without quantum memory. And the problem is for synchronization, in fact. Because when the satellite, maybe I will use, so I go in the future of my presentation. It's, where is it? Here. So this is what we have published. So this is, let's say, the most simpler but non-trivial problem. So one satellite, 2 stations. Okay, and so we are French and we are working with French researchers, so we were thinking about connecting Nice and Paris, because our colleagues are there and we are developing ground stations there. And so the problem is that compared to what people are doing in the lab, the satellite is moving very fastly. So 20 roughly this is 20,000 kilometers per second. So you have Doppler effects, you have many problematic effects, many perturbating effects. And if you think that the satellite is very close to Paris, that means that the first photons that goes to Paris will arrive at Paris before the photons that goes to Nice. Okay, and so you have a non-symmetric geometry, and so that will be very hard to perform Hong-Mandel experiments in real time without quantum memories. So the quantum memories will be required at least to compensate this asymmetric effect. So when you're looking at papers published by Delft group in the Netherlands or by Hugues de Ritmaten, or so generally, so Hugues de Ritmaten in ICFO in Barcelona, they are able to compensate the asymmetry, and they are able, in fact, to log the experiment such that the photons are arriving at the good time at the good place. But here the source is moving very fastly, and you have to deal with many effects that are that disturb the experiment. So that's why the quantum memory will be very interesting to compensate for compensating these effects.
Just maybe an even more naive question. Why is there such a need for synchronization in terms of when these two packets arrive, so to speak?
Yeah, okay. Yeah, because now I go back. Yeah, okay. Because, as I said, okay, so maybe I come back to my presentation and I will develop. So,
yeah, sure.
I was speaking about quantum teleportation, and so I'm pretty sure that a lot of people are not aware of what is quantum teleportation and what is a quantum information network, and so I can explain here. So first, when we speak about quantum teleportation, what we teleport is the information and not the physical particle itself. So there are no matter teleportation. This is only the information, not the system itself. And we cannot go faster than the speed of light because we will need a classical channel to exchange information. And this is not a copy of the state. When you teleport the information of a particle, you destroy the information of the initial particle and you teleport it to another particle. And the teleportation use entanglement. And so entanglement, as I said, it was the Nobel Prize in 2022, sorry, because we have shown. So when I say we, I mean Alain Aspect, the French researcher. He showed that two particles can be, in fact, the same quantum system, and that's very strange, because when you entangle two particles, you can send particle 1 at left, particle 2 at right, and very far away. And what Alain Aspect showed in his experiment 40 years ago now, he showed that when you measure one of the two particles, the other one, wherever is particle, will be affected by the measure of the second one. So this is the same system from the quantum mechanics point of view, but in the space and time there are two different particles, and that's very strange. And so here this is the Bell state. So when you have two particles, you can entangle maximally these two particles in 4 Bell states, which are mathematically given by these equations. And what our colleagues are doing, and what we are now doing in Thales-Alenia space, we are generating entanglement using nonlinear optical effects like SPDC, so spontaneous parametric down conversion. And so we are using nonlinear crystals, and when you pump nonlinear crystals, one photon can give 2 photons. So you can generate twin of photons, and these twin photons, when they pass into a Sagnac interferometer, you can untangle them, because you don't know if photon 1 took the right path or the left path. And so the 2 photons become entangled, and then you send them to optical terminals. So this is the picture here. You have two optical terminals on board the satellite, and so this is the source that generates entanglement. And then you send the photons to ground station 1 and ground station 2. And so here, this is a picture of the misuse entangled photon source that generates the state psi plus. And so now, okay, I come back to your question about the entanglement and why we cannot communicate faster than light instantaneously.
Mm-hmm.
So when you want to perform a quantum teleportation, you have to think that Alice, for instance, has the state 1. So this is a photon, state 1. And Alice will teleport this photon to Bob, which will arise here. And so, to do this, since Bob is far away, we will use an intermediate source that generates entangled photon source, so entangled photon pair. So here,
this would, sorry to interrupt here, but in the context of the quantum information network, this entangled photon source would correspond to a satellite, or would that be some ground-based system?
Yes. Okay. So this is architecture matters to think about if this is at the ground or if this is a satellite. But yes, you're right. This could be a satellite that emits the pairs, the entangled photon pairs 2 and 3. And so what we are doing, in fact, we are doing a Ongu-Mandel experiment here with a Bell state measurement. So photon 1 and photon 2, they arrive at the same time at the same place. And when I say at the same time, so it depends of the laser you're using for photon 1 and 2, of course, because a photon has a half width at half maximum, and it depends of this. And so typically to give you an idea of the time, so the time is around 100 picosecond. So if they do not arrive at this place at the same times plus or minus 100 picoseconds, that will not work. And that's the problem. So there are huge synchronization requirements to do this. And the Ongu-Mandel, this is an interference between the 2 photons, and then you send them to analyzer and single photon detectors. So the photons will click a single photon detector. And this ID has been developed in the 1993 by Bennett. So this is a theoretical paper. And the first experiment has been performed in 1997. So many people in the labs are doing quantum teleportation. So this is not science fiction. This is not a fiction. This is a reality in the lab. And then when you will do what we call a Bell state measurement of photon 1 and 2, the information of photon 1 is teleported into photon 3 that arrives at the Bob site. Mm-hmm. And to do this, so here this is a mathematical description for those who are interested about the calculation. So
before we go into that, maybe I can jump in with a couple of questions. So two questions in particular that I have at this point. The first one would be, I accept the fact that we need to have a very synchronized arrival time for photon 1 and 2 at the beam splitter, because otherwise you're not going to observe these effects, and we can perhaps get into those effects and exactly what they mean for the system in a second. But I understand that there is a requirement to have very precise time synchronization on that side. How come you also need to have very precise time synchronization with the arrival of the photon number 3 at the other system. I would expect that if you have a satellite that comes that you want to time this with, essentially, you need to have it very well timed with the transmitting qubit that you want to then send to Alice, or to Bob in this case, and the arriving photon from the satellite. But I don't see the requirement for the two beams of the satellite, so to speak, to be synchronized themselves. What's the reason for that?
Okay, yeah. So because here the system is this is an embryonic system. This is a very simple system. So you can think. Okay, I'm going to slide just after. So you can think that now you have two satellites. So two untamed photon source. So photon source 1 and 2, and then you have to think about many beams coming from the space segment from two satellites that should arrive at the same time here. And if photon 3 and 4 they do not arrive at the same time at the same place, you cannot perform the Bell state measurement. That will not work.
Okay. And given that the time requirements for synchronization are so slim, you need to effectively have a quantum memory, because timing the transmission of those photons would be too complex of a task.
Yes, exact. So typically photon 3 can go into a quantum memory and be stored to compensate the delay, such that photon 4 arrive, and then you push the button of the quantum memory and say, okay, photon 3, now you go out, and then the photon 3 will arrive at the same time on the Bell state measurement than photon 4, and then you can perform the Unge-Mendel experiment here. The Bell state measurement.
Okay.
Yeah.
The second question would be, the second question, if we go back to this slide exactly, is conceptually why this beam splitter interference that we're going to have between photon 1 and 2 results in us teleporting the information of qubit 1 to essentially where qubit 3 was located. Do you have, so you have a mathematical description of that here. Do you have a conceptual explanation for why this phenomena occurs? So I understand that the, I'm going to mispronounce this, but the Unge-Mendel effect causes the photons to exit in the same, let's say, trajectory, is my understanding, from the beam splitter. So there becomes a sort of interference pattern between these two photons as they enter. But what is the correlation between, or the relationship between that finding and the fact that the information of qubit 1 is then teleported?
Well, okay, so in the Unge-Mendel, so that's true that in the Unge-Mendel, initially what they showed is that when the photons arrive at the same time at the beam splitter, they all together go out in the same channel due to quantum interference. But in fact, that really depends on the state that arrive on the beam splitter. So this is a dip. So here, this is the initial experiment of Unge-Mendel, and you see that. So this is small, but this is the time in. This is a time difference, the time arrival difference in the horizontal axis, and when the time horizontal difference goes to 0, then you have a dip. So the dip, this is a dip between measurement in channel 1 and measurement in channel 2. So this is a correlation between the two detection of the two channels. So this is called a coincidence, in fact, a coincidence in the measurement. And the coincidence goes to 0 if you have no noise, of course, in the perfect case, because the photons goes out in the same channel. But this depends on the state that arrives into the beam splitter. So for instance, so the mathematical description of the system with 3 photons is given by this state. So here this is phi, and phi is a tensorial product of psi 1 and psi 2 and 3. So here I have assumed that the untamed source, the untamed photon source is generating psi minus, and so if you do psi minus times psi 1, what you get is this state phi, and this state phi you can write it with the 4 Bell state that I wrote in the previous slide. And so what happened is that these 4 Bell states are in fact the Bell state for photon 1 and 2. And so when they will be measured in the Bell state measurement device, you will project the part. So this is part of the wave function of the state. The part for photon 1 and 2, you will project it into one of the 4 Bell state, and then for photon 3 will remain one of the line. So there is 4 lines, and depending on the results you will observe here, you will project the wave function, and you will have at the end the photon 3 in one of the state here. So I can be clearer when I show you this experiment, this measure. So for instance, so here, if it clicks on the horizontal, so H and V, this is for horizontal and vertical for the polarization of the photon. If you have a click on the horizontal detector here at left and a vertical detection at right, that means that you have projected psi minus 1, 2 into psi minus 1, 2. So that means that you have selected the red line, and the photon 3 will be projected into the state of exactly what Alice has sent. So in the state of psi 1. Okay, so in fact here everything is perfect because the information of Alice has been teleported into the photon that arrives at Bob's side. But the problem is that you have to announce the results of the measurement here, you have to announce with a classical channel. So here there is an antenna, or it could be also an optical communication, and you have to send this information to Bob. And then when Bob knows that it has clicked in this way, that means that the teleportation has been performed, and there is no correction to be done on photon 3, and the teleportation is effective. But sometimes...
Okay, I understand the need for the communication link, the classical one, between these two nodes.
Yeah.
What I didn't quite understand is, given the 2 clicks of the Bell measurement that you have, how do you map that necessarily to the first row of the state description that you have at the bottom right?
Yeah, okay. Yeah, because here this is a psi, so this is psi minus, and psi minus, okay, in terms of 0 and 1, but it could be translated into H and V. So this is a state where the first photon is in H and the second is in V. So if photons 1 has clicked in horizontal state, that means that the other photon will be found in the vertical state. So there is a correlation between vertical and horizontal. And the minus here is why the photons are not going into the same channel. You remember here I said that initially Ungu Mandel, when they did the experiment, the 2 photons were going towards the same channel at the output. But in fact that depends of the income state. So if the incoming state has so it depends if it's symmetric or asymmetric, in fact. And since you have an asymmetric, so the minus here introduce an asymmetry in the state, and since photons are bosons, the asymmetry of the wave function should be symmetrized at the measurement. So it's a bit technical, but in fact the photon 1 is going to the left and photon 2 to the right. This is because the photons are bosons and because the incoming state is asymmetric, and so you have a compensation that in fact leads the photons to go not in the same channel.
Yeah, so the same channel effect is only observable when the 2 incoming photons are indistinguishable, right?
Yes.
That's the principle you're alluding to.
Yes, exact.
Okay.
Yeah, and so what I mean is that if the untanked photon source emits psi minus, then if you have a correlation between H and V from left and right, then that means that the teleportation is effective and you do not have to correct the state. But sometimes the two photons can go to the same port, and here it is only possible if you have measured the psi plus state, because the state is symmetric. And so this is the Young-Mandel experiment. So both photons are going through the same channel at the output, and so you measure H and V at left, or H and V at right. And so this is the signature of the measurement of psi plus, in fact. And so if you measure this, then you send the information to Bob using the classical channel, and Bob has to perform a correction of photon 3. And so with photons, you can use half wave plates to correct the polarization, and then you will flip the sign minus into a sign plus, and then the teleportation is effective. So in this case, when you measure it, you have to apply a correction to photon 3, and then the teleportation will be effective. And the two lines, this is complicated because phi minus and phi plus, they have the same signature, and you cannot distinguish the signature of these two states, and so that means that you can teleport just 50% of the time.
Okay.
And that's a problem. So in the perfect case, it will work half of the time. And to go back on what the Chinese did in 2017, they have performed a quantum teleportation from ground to space. And so that means that in the misuse satellite, they have included a quantum analyzer and the single photon detectors on board, and they have shown that they have played with many states. They have prepared horizontal, vertical, plus, minus, left and right states. So six states, and they have teleported these states toward the satellite, and they showed that the fidelity were up to 2/3, and so that's the signature of the quantum teleportation. If the fidelity is above 2/3, then you definitely have a signature of a quantum state, and they published it in Nature. So they also have performed such experiment with misuse.
Okay.
Yeah, and so now I come back to your question about synchronization. So if you need to connect people that are very far away, then you need to use many untanked photon sources, and so you have to swap the entanglement. So this is called an entanglement swapping here, where you have photon 2 and 3 that are entangled, photon 4 and 5 that are entangled, and then when you perform a Bell state measurement with photon 3 and 4, photon 2 and 5 become entangled. So it's like if photon 2 and 5 were coming from an entangled photon source that does not exist here. So you can swap the entanglement and then entangle photons at larger scale and connect Alice and Bob. So Alice could be in New York and Bob, I don't know, in Japan. And then it could work in principle. So using entanglement swapping, you can connect two users that are far away, and then you teleport photon 1. So you perform a Bell state measurement between photon 1 and 2, and then the quantum information of photon 1 will be teleported into photon 5 that arrives into Bob.
Do you have a rough view of how many of these linkages are possible currently in the lab? So I'm expecting that the more satellites you would introduce into the system and the more of these Bell state measurements you would have to perform along the way, the larger the instability and inaccuracy essentially of this system would be. Do you have a view of how far you can push this, roughly speaking, before it becomes unfeasible for these kinds of applications that we're considering now?
Yeah, at the moment, I do not have the answer. Now, I'm system engineer, so we are not researcher on labs. So I think this question belongs to researcher on labs at the moment. What we are doing, we are not in competition with them. What we are doing, we are thinking about the system that could be developed. And I know that people now are part of the system. So, for instance, I will show you I can show you now. So when I show the picture to QINs, for instance, they are our customer, QINs and ESA. So QINs, this is a National Space Agency in France, and ESA is a European Space Agency. They paid us to work on this, and typically one question is, does it exist? So you have a system that is a line. Alice is connected to Bob, and between Alice and Bob there are many Bell state measurements, quantum memories, untanked photon source, and so on. But does it exist somewhere? So that's the question. And I can answer yes. So if you look at this wonderful experiment at ICFO close to Barcelona, so this is the Hugues Matten group. So typically what he did in 2021, so he has two untanked photon source, so here and here. He has a Bell state measurement between both, and he has two quantum memories. And what he did is exactly the perimeter in the dashed line here. So he has a Bell state measurement, two untanked photon source, and two quantum memories. They are not mentioned here explicitly, but they are present in the experiment. And he showed that it was possible to untangle the two quantum memories when performing a Bell state measurement here between the two sources. And typically the storage, to come back on your question, was 25 microseconds. So we are at the beginning, let's say, and still this is a very complex experiment because of synchronization and quantum device to work all together. So this is like an embryonic system, which is a part of the system I described before.
Okay, are you able to give a conceptual explanation for what happens here? Like, I know there's a lot of details in this figure that we could get into, but just on a very, very high level, we're trying to entangle these two quantum memories. And what is the underlying principle for that kind of entanglement? Is it very similar to the way you would entangle just a set of photons to begin with, or is the principle here fundamentally different?
No, I think, okay, when we say we entangle the quantum memories, in fact, that means that we entangle the photons that were entering into the quantum memories. So when the photon enter into the quantum memories, what you have an excitation of an electron into the atoms, and this is this part that you entangle, in fact. And from the theoretical point of view, I think this is very similar to what I discussed before.
Okay.
So this is due to the entanglement. You have entangled two photons that were not initially connected, but still the information has been encoded into the electronic excitation, but this information is entangled. So that's my point of view.
Understood.
Yeah, and so in our publication, so we have drawn a network like this, where you can see that Alice and Bob are at the ground, and they are connected into a local network, so with optical fibers. And here there is a space connection, so we call this a quantum ground station, that receive photons emitted by satellite 1 and 2. So there are three quantum ground stations here. And so this is a path, so you have to find a path to go from Alice to Bob and to teleport the information of Alice toward Bob. And so that's this is exactly the topic we are working on, to think about the interconnection between the space segment and the ground segment and the synchronization of all these optical qubits.
Mm-hmm. What's the purpose behind quantum ground station 2? So in the middle of this figure, QGS2, you have a signal that then goes from the first quantum ground station through the second one to the third. As we discussed before, you could potentially have two satellites that would communicate directly. What's the advantage of having a intermediary quantum ground station?
Yeah, okay, so this is architectural trade-offs. So typically, what you say you have two options. You can either connect satellite 1 and satellite 2, so they will receive, they will exchange photons, and you do not need to use a space to ground node. But to tackle this trade-off, you have to clarify which type of architectures, what are the orbits of satellite 1 and 2, when they will see each other. So in fact, this is related to the density of the constellation. The more you have satellites, the easier you can connect them in a certain sense. And I agree that this point of view could not be the better one. Maybe satellite 1 and 2 should be connected, because in space you do not have the atmosphere and clouds. So that's very practical to exchange light between satellites. Definitely. But
the key benefit of this kind of architecture that we're looking at now is that quantum ground station 2 serves as a form of safeguard against having satellites that are not overlapping very well. Is that the main principle why you would have quantum ground station 2 in this figure, or is there also other ones?
Yeah, it could be. It could be, but in fact this is a routing problem where we have to think about the better path to select. So what I can tell you is that the satellite will be connected for sure. When you have a constellation, you need inter-satellite link, at least for the command, because when you send a command to satellite, you want the command to route into the constellation. This is very practical to do this. But it could be with radio frequency, or it could be done with optics. So when I say optics, I mean classical optics. And now, if we have classical optic links, the step to go to quantum optic links is maybe not a big step. And so we are discussing such architectures. But for sure, this is a very good remark. We can think about a path between the satellites. Yeah, and so here I recall that the Chinese has performed the entanglement distribution from misuse to two stations, and so they have a key performance indicator, which is the violation of the Bell state inequalities, and they have shown that this is definitely we are definitely in the quantum regime where this quantity is higher than 2. So that's the signature that we have indeed received untanked photons at the ground.
Okay.
Yes. Okay, and so just a few words. So I cannot tell you exactly what we are doing and all the architectures we are developing, because this is confidential. But we have a very interesting project that is called QINs, for technological developments for space-based quantum resource distribution, and we are targeting to develop. This is a technological phase where we are developing many devices, many quantum devices, like a quantum entanglement source, also a source for QKD, quantum source for QKD, and also the ground optical terminal, the space optical terminal, and other devices to reach the technological readiness level 6 in 2 years, and we are working hard. So with all these partners, there is Airbus who is working with us, Alpao, Aurea, Eutelsat. So there are many actors. Sigma works for synchronization. There is also so we are not all French. There is also Austrian, the QT Labs, and our partners Infini and Lipsys, who are researchers, and the customer, the people who paid for this is QINs and ESA. They support us. They are our support for this kind of activities.
Mm-hmm.
So I don't know if you have any question about this topic.
Not the project as such. I have more questions potentially on, well, I have a lot more question actually on quantum information networks in general. We are over time quite substantially though. So I think perhaps we should cut it here. I don't know if you would have time to do a follow-up discussion because I also have to drop. But if you do, that would be super interesting to dig into some of the more further details of that.
Yeah, okay. Okay, so...
Okay.
We
awesome.
can stop here. So just to show to people who are interested that the next to discuss is to speak about the dynamics in this topic, the actors, who is working on what, and what is the future of space-based quantum communications. So the conclusion of this discussion is that the satellite is mandatory for such new quantum information networks we want to develop. Thales Alenia Space is a major actor on this topic. And in France, we have support from the European Commission in the Euro QCI project. And so this concerns not only QKD, also quantum internet. And the topic is very attractive, and our group is growing fastly, and that's a good point.